right, these are the Unit 10 electron bonding and shape notes, and this is part 1, which will be about ionic bonding. You might remember that we talked about ionic bonding back in Unit 5 as well, but we have talked about ionic bonding before. Okay, electron configurations, that was in our last unit also. So when we talk about electron configurations and ionic bonding, the first thing that we have to talk about is valence electrons. If you remember, valence electrons are those electrons in the highest occupied energy level of an element's atoms. And we went through the trend of valence electrons on the periodic table. So to find that number of valence electrons, we looked at the element's group number, which was the number next to the letter A at the top of the column. So all of the elements in the first column, starting with hydrogen down, okay, through francium, all have 1. And then all of the elements in column 2, which starts with beryllium down through radon, they would have 2 valence electrons. So on through the periodic table, all the way to the last column on the right, which would be starting with helium and ending with, when I said radon a minute ago, Ra is radium, not radon, sorry. And then going down through radon, those have 8, okay? And remember that they are, the 8's the magic number, except for helium. Helium only has 2, so that really could have just an exception drawn there that said, you know, that helium has 2 instead. So that's just something to be aware of. All right, now when we're doing an electron dot structure, there's a system of arranging the dots that represent just the valence electrons. And if we look up argon, argon has 18 overall electrons, but it's in column 8A. Since it's in column 8A, it gets 8 dots around it. So when we put those dots, we put 1 on each side like a box, and then we partner those up, and we can make them pairs of electrons. Okay. These can also, this was actually developed by a scientist named G.N. Lewis, and so we'll also sometimes refer to these as a Lewis dot structure. So write the electron configuration for phosphorus. Phosphorus is number 15 on the periodic table. And the electron configuration would start, remember, with 1s, and then there's 2. And then it would be 2s, and then it would be 2. And then it would be 2p, and there are 6 squares in p, so that would be 2p6. And then we would go down to row 3, which would be 3s, and we would put in 2. And then we would move over into the 3p, and that 3p we would move 3 blocks into. And so that electron configuration would be 1s2, 2s2, 2p6, 3s2, and then 3p3. Now, when we did it as an orbital diagram, we would do it like this. And remember, each one of these would get 2 arrows, 1 up and 1 down. And then we would fill 1, 1, 1 of the P, and then we'd go back and fill them again. And then this would get 1 up and 1 down for the S, and then we would do 1, 1, 1. And the reason we do those 1, 1, 1s, remember, is because of Hund's rule, saying that everybody gets 1 in an orbital before we go back and partner them up with a second. Okay, we fill all these lower energy levels first because of the fact that that is the off-ball principle. And then we do 1 up and 1 down because of the Pauli exclusion principle, which said that they have to have opposite spins. So that would be from the previous unit when we talked about electron configurations. Now let's write the Lewis dot structure. Well, the Lewis dot structure is, remember, just the valence electrons, so it's just the electrons in the highest energy level. Well, the highest energy level is the 3rd energy level. So we would just be doing the 5 electrons that are in the 3rd energy level. So we would do dot 1, dot 2, dot 3, dot 4, and then dot 5. So we would have 5 dots around it. Okay, and remember, the dots represent just the valence electrons. Now, as we continue on in this particular unit, we'll talk about the octet and or the duet rule. And the octet rule is when forming compounds, elements are going to tend to achieve the electron configuration of a noble gas. And that is because they either want to lose electrons or they want to gain electrons, or they want to share them. That's all that elements ever want to do. They want to either gain, lose, or share electrons so that they can be like the noble gases. Remember, the noble gases are the cool kids in the periodic table, and they have full valence shells. Okay, and so that's why everybody wants to be like them. So metals will typically lose electrons and form positive ions, which are cations, which we've learned before. Okay, and I'll write that there. And then we have, so like sodium would be 1s, it has 11 electrons in it, so it would have 1s2, 2s2, 2p6, and then it would have 3s1. Well, the closest noble gas to sodium is neon, and that would happen if sodium lost one, okay? Because neon only has 1s2, 2s2, and 2p6, okay? So if a sodium would lose that single electron, then it would now become sodium positive 1. And notice, now it's exactly like neon. So that was able, because of the octet rule, to be able to lose that electron. Now, nonmetals, on the other hand, are typically going to gain electrons to become negative. So oxygen normally has 8, so it would be 1s2, 2s2, 2p4, okay? Or, yeah, 2p4. And then, so neon's the closest one, and neon has 1s2, 2s2, 2p6. So sodium really needs to gain 2 electrons to become like neon. So that's what it does. When we gain those 2 electrons, we now make it the ion oxygen -2. So you might remember when we did the oxidation numbers across the top of the periodic table, and we said, we gave them their charges, and we said like the first column was a +1, the second column was +2, and then the column 3A was a +3, and then we said that the fourth column would be a plus or minus 4, depending on what it did, and then we had -3, -2, -1, and 0. And those oxidation charges are actually there because of this rule, okay? So we taught you that trend before we taught you this rule, all right? So the electron dot symbols, or the Lewis dot structures, can be used to represent those ions as well. So sodium has 1 dot, chlorine would have 7 dots around it. And then fluorine would have 7 dots around it because it's in 7A. And then magnesium's in 2A, so it would have 2 dots. Oxygen is in 6A, so it would have 6 dots. And then aluminum is in 3A, so it would have 3 dots. So in order to represent these ions, sodium would lose that dot and become a +1. Chlorine would gain a dot, and so it would be a -1. Fluorine would gain a dot to make it 8, so it would become a -1. Magnesium would get rid of those 2, so it would become a +2. Oxygen would gain 2, so it would become a -2. And aluminum would get rid of those 3, so it would become a +3. Okay, so that's how we would represent these as electron Lewis dot structures, or electron dot symbols, as ions. All right. So when we do ionic bonds, you might remember ionic bonds are going to form between a cation and an anion, and that's a positive and a negative ion. And it's really a transfer of electrons. So those are the key words right there. It's a cation and an anion. It also could be a polyatomic ion. Those are the other things. And it's a transfer of electrons. Those are the key words there. So when we have binary ionic compounds, it's generally just a metal and a nonmetal bonded together. Okay, and so really sodium gives its 1 electron that it has over to chlorine. It makes sodium a +1 and chlorine a -1. And now they are bonded because of that transfer of electrons in an ionic bond. That creates table salt. So when sodium reacts with chlorine, what kind of compounds formed again? Ionic. Okay. Is there a transfer of electrons? Yes. And the reason sodium and chlorine, when they make a compound, it's a metal and a nonmetal. Remember, metals are on the left side of the staircase, and nonmetals are on the right side of the staircase. And then the metalloids, except for aluminum, are on the staircase itself. Is there a transfer of electrons? Yes, because sodium becomes a positive 1 ion and chlorine becomes a negative 1 ion. So yes, there's a transfer of electrons. And using the Lewis dot structure to show how that would happen. And so we would have Na, and then we would have Cl, and then we would have Na just as a positive, okay, because that 1 would get transferred over to chlorine. I hate to move this. When it transfers over like that, we end up with, sodium as a positive and chlorine as a negative. So that's how we would show that in its Lewis dot structure. All right, so some properties to remember about ionic compounds. They're solids at room temperature typically. They have a crystalline structure, which really means it just has a crystal lattice, okay, because of how they align with each other. And they have high melting points. So that's just a key kind of thing to remember that they have. All right. Melting point of salt, by the way, is 802 degrees Celsius. So that's really a high melting point. All right. This concludes part 1. Oh, actually, let's do a couple of examples. Potassium and chlorine. So potassium would be K on the periodic table, and it is in column 1A, so it would have 1 dot. And chlorine is in column 7A, so it would have 1, 2, 3, 4, 5, 6, 7 dots. So when we combine them, that would be a K positive 1, and then it would be a chlorine now with 8 dots around it. And lots of times when they get a dot from somebody else, I'll make that electron an X, and then we do a negative 1 because it becomes a negative 1. And that would be the actual electron dot structure of potassium chlorine and chlorine together. That would create potassium chloride, and the compound would be written as, remember when we wrote compounds, we said this was a positive 1 and this was a negative 1. So when we crisscrossed or did the drop and swap, it was KCl. Okay? All right, if we take calcium, calcium is Ca, and it becomes a positive. It has 2 valence electrons. And then chlorine is Cl with 1, 2, 3, 4, 5, 6, 7 valence electrons. All right. So when chlorine would give one of its electrons away, that would when calcium would give one of its electrons over to chlorine, it still has one to give away. So what would happen is we would need another chlorine to go ahead and give that other electron to. And so that would now mean this one would come down here. Okay, but we don't have to show it that way. Another way to think about it is calcium would have become a 2 positive, and then chlorine, 1, 2, 3, 4, 5, 6, 7, and then I would put 8, and it would become a negative 1. And so that should tell us that we would need 2 chlorines. So to represent that, lots of times I just do it as, I do Ca, 2 positive, and then you'll do 2 times, then you'll do the chlorine, 1, 2, 3, 4, 5, 6, 7, 8 to the negative 1 in parentheses. And so if we wrote the formula for that and we did our crisscross, we would remember that it's Ca, positive 2, chlorine, negative 1. So if we crisscross those down, that becomes CaCl2. All right, so that's a check because we have 2 chlorines represented for every 1 calcium in our drawing. All right, so that's going to conclude right now our notes for this. Hope you enjoy. If you have questions, ask me. We can talk.